You guys ever wake up and when you awake, are you tired or are you pretty much ready to go?
Tired.
Man, me too. But you know what I find helps on a daily basis? Red Bull! It gives me wings to get throughout my day. The day flies if I start my day with this super high sugar drink that's probably not very healthy for me in reality. All right. Here we go. 1.10, mathematical modeling. We are going to be looking at types of variation. Now, a lot of the real world you can model. And in fact, I would say the usefulness other than like pure knowledge of mathematics is that ability to model the real world. Some of you guys have me multiple times per day. Do we have a class that really kind of focuses on here's how we model the real world with mathematics? It's physics, but it turns out it's also pre-calc because we're going to model the real world with mathematics. And in here, we are just going to look at the mathy side of it, which means all the concept of stuff might just go whoosh, and you don't even care or know why it works this way. We're just going to make the comments that it does work this way. Okay. Now, going through stuff. I've done this a few ways historically. We're not going to go through the least squares, residual lines, and regression lines and all that. So instead, what we're going to do is we're going to list out all the types of variation and the different types of models that we might use. And then we'll do some examples at the end, and we'll see maybe it's not as terrible as it might look if we just do one at a time. Now, right off the bat, the first one that we write is easily going to be the wordiest. So our focus today is on these types of variation. Now, for your purposes, we have 1, 2, 3, 4, 5 different types of variation that we're going to look at today. And they're all okay models. As long as we understand the language with it, they're pretty easy to make sense of. So we'll start with the easiest, if that's cool with you guys. Our first type of modeling, and first of all, mathematical modeling, just can somebody tell me what does it mean? If I'm making a mathematical model, what does it do? Talk with your neighbors for like 30 seconds. I'm going to call on somebody random. What is a mathematical model is the question at hand. Show it the way to model real world situations and the way that we can predict data. Right? That's this song. Number 6. Who dat? Sean. What's a model? Mathematical model? Does it have to be a graph? So, doesn't have to be a graph, but you could certainly model with graphs. When we talk about modeling, somebody have anything else to add other than just saying the graph? Louder. The picture. So maybe it's a picture if you're thinking like in physics and stuff. Absolutely. In mathematics, we could graph, but if you want to make a graph, what are your directions that tell you what graph to make? Like if I said, hey, here's some equation, graph it, you probably could, right? To get that graph, you just needed the equation or the function or whatever the case is. Turns out all these models, we're going to look at them as graphs is fine, but I think of functions or equations that determine how one relationship changes with another. You could represent it graphically, but we can also do it with an equation and things like that. So we are just looking at ways to make predictions given enough data to make a model that hopefully we can use. So our first and easiest type of these are our linear models. And this is going to be the only one that splits into two little pieces. We have two different linear models that we're going to look at. And they're pretty similar in reality, but they're not too crazy. Now, in general, the first one, you guys have seen it, you love it. If I asked you to write the equation of something linear, y'all are probably going to give me the same follow-up. Y equals mx plus b. Okay, we've seen it. Typically, though, if you're going to take the time to write it, do you agree that we all just kind of work under the assumption that b is probably not going to be 0? Because if it were going to be 0, we'd have no reason to write it. Now, that hooks us up, though. This is the super mathy model where typically it's not b. We're going to make it easier than this, though. Because if b were 0, this equation gets simpler. So we're going to do the following for each of these. The first, and we're just going to jump right in, we're going to give ourselves what is known as direct variation. If I say something varies, what does that even mean? To vary means to change, right? So if I think of something changing and its impact being directly related to something else, there's some pretty easy things to go through. They're not always associated throughout the entire life, but check this out. Imagine in front of you is a brand new infant, just born. Its size and weight directly relates to how much time it's been alive, right? The longer that infant lives, the bigger it gets, typically, pending like if you ignore some maybe catastrophic health issues or things like that. But do we all agree that babies get bigger with time pretty much directly? Okay. When we deal with that, that is an example of direct variation. So the simpler model than just this, we're going to write the following. The model for direct variation, super duper easy. Instead of y equals mx plus b, we're going to simplify it. Y equals kx. Where, and all that we're going to say about this is that this value k gets a special name. We'll just specify that k is the constant of variation. I'm going to underline it. I'm not going to give you guys vocab when we get to this assignment. Not sure if we'll get the assignment today or not. We'll see. K is the constant of variation. For all intents and purposes, is this any different than y equals mx plus b? What do you think? Instead of m, we're using what? K, and then what's b if we just don't write it? 0. So this is the same formula. It's just simplified a bit and changed letters, but there's a reason that happens. Okay, moving on. This part is the bigger, I would say more important part, especially from the beginning. We're going to have different statements that are equivalent to each other, and I want to make sure that whatever route we go through here, we are going to stay consistent with each new model that we see. So equivalent statements, of which there are going to be 4 different ways that we can word this. Okay. All right, rather. I don't know why I would underline it. Here we go, equivalent statements. The first one. If you read this, we can certainly just say y equals kx, and that's maybe the simplest way to do this. Do you think there's any restrictions that I should put on k so that this isn't just the most boring thing ever? K cannot be 0. Otherwise, this is just y equals 0. It's just a horizontal line. It's boring. Nothing meaningful comes out of it. Now, notice this statement has already showed up. It is just our model that we're going to use. It is a one equivalent statement that we'll have. Another way to do this, our second equivalent statement, the direction really matters. I'm going to say that y varies or changes, but I'm going to write the word varies directly. And I like to use the word as, but you may see it as with. What variable changes as, like y changes as a result of changes to what other variable? In x, you're right. Does it feel more natural to say y varies directly as x or with x? I like as because as x changes, so does y. With would be fine here though. So y varies directly as x. All that this means is it's going to fit in this model. And we'll see that language, and we'll see it a lot in physics. We'll see it today in some physics examples. This language is really, really specific. Y varies directly as x says this formula. Now, off to the side, don't write this one. I just want to think. Let's say that what's something that changes directly with something else? Can we all agree that in other places, temperature varies with time, especially for the morning? So if I said temperature, and don't write this down, we're just talking, varies directly, we'll say VD, with or as time. Could you write that in this statement? What is the variable that's changing, or the independent? Time, and what's the dependent? So if we're looking at this, and this isn't necessarily a true statement, would you agree that temperature varies directly with time? If I just plug in, it just looks like this. K or temperature varies directly as or with time. I'm just making sure that the language is there so that if I switch it around, if I said X varies directly as Y, it would be X equals KY, and the order changes. The language matters there. We will see it like 4 or 5 more times. All right, hustle back. Thank you. Boom. Moving forward. Another way to word this. It does show up. Y, one might say instead, is directly proportional to X. These are synonyms, and that's not the right word because they're actual full statements. They're equivalent statements. Synonyms is the word version of that. I can either tell you Y varies directly as X, or that Y is directly proportional to X. They mean the exact same thing. Both of those languages are just going to be Y equals KX. The last one that we get to deal with here, the last equivalent statement. I lied. There's 3 of them. These. We're done. Piece of cake. Now, I want to suggest something. There's another type of direct variation that we might want to write down, but I think if we just talk about it, we might be okay. If I said Y varies directly as X, it's this equation, right? So all I need you to do is I'm going to say Y varies directly, and that's again VD, with the square of X. See if between you and your neighbors, you can tell me what that formula should be. We have direct in it, which I have direct in those other ones. What's the only thing that changes? Marginalia is fine, or just language is fine. How would you write Y varies directly as the square of X using my direct variation formula? Would you erase that before you do it?
No, I'm just trying to just
Okay. If I just didn't say with the square of X, if I just said Y varies directly with X, it'd be Y equals what? KX. All right. Can you write me the square of X? What does that even mean? X squared. When we look at Y varying directly as the square or the cube or the root, it doesn't matter. We can simply just add this in and say, oh, I know that this word, and I should make it a real word, I know that this word and this word are happening, and I can make sense of them. When we do this, we can write these exact same things and simply add as in with nth power, but I don't know if we need it. If I just say Y varies with X, directly with X, KX. Y varies directly with the cube of X would be Y equals KX to which power? Cube. Do we need to write a whole nother section with all these words just with the nth power instead? Okay, if we do need to wind up adding it, we will. I'm going to insert right here, not insert, nth powers exist. All that means is if it's not specified, I assume it's to the first power, but it could be the square, the cube, the fourth, the fifth. Don't care. Doesn't matter to me. Okay. Direct variation is the first model that we deal with, and it's my linear model. We'll do problems like these. We'll see it immediately with science stuff. Let's check out a little bit more complex of a model. If it's linear, it's a line. Non-linear stuff exists, though, and it happens all the time. As we go through here, I'm feeling green with this one. We're also going to talk about our inverse variation. So we have direct variation, and we have inverse variation. All right, here's my suggestion. We're already writing these things. We're essentially just going to do this for every model without having to write all the same stuff. So we'll see if I need to clarify more. If I do, please let me know immediately. The first one, I'm going to say inverse variation, and I don't love this language necessarily. The model that we deal with, Y equals K over X. Probably worth mentioning it. K can't be 0 because that would be boring, and X can't be 0 because that wouldn't work. So we'll put it here. K is never going to be allowed to be 0 in any of them, just so you guys are aware. Now, we've seen these before, and I'm trying to remember if we talked about them in here or if it was just physics, but that's almost a complete overlap. Linear, what's an inverse relationship do? As one increases, the other one decreases. And is it a line? We'll look. So check this out. It's varying still, but it's not varying directly. Instead, I'm going to say y varies, and these are all my equivalent statements. Y varies how with x? Direct variation meant directly. Louder, Angel. Inversely. Y varies inversely as x. The second you see varies inversely, you know that it's this equation, and your essential job is just going to be to find k, but we'll see that in a few minutes. Okay, superpowers of deduction. We said on the first one, y varies directly. We could also say instead that y is something. Look at your first one. Y varies directly as x led to y is blank as x, or with x. Direct. Hey, so we're just going to change it. Instead of directly proportional, an inverse relationship should be how proportional? Inversely proportional. To x. 3 statements, same thing. And we will see very specifically where this language shows up. All right. So we have direct variation. We have inverse variation. Couple more. In fact, 2 more that we're going to look at, and then with just examples, which there's not going to be homework tonight. Today's Wednesday? Okay. There will not be homework tonight. Are you guys good with inverse just written here? Okay. Moving on. This one, we're getting real crazy. Instead of just having inverse or just having direct, man, we're going to get wild. And we're going to talk about combined variation. Now, this one is a little bit harder to write all these things out, but we're going to do a quick example. We've seen 2 types of variation so far, right? Inverse and direct. So we'll see an example where this works, but if we look at this, I'm going to write an equation here, and I'm going to say in parentheses, since we've only looked at those, this example indicates direct and inverse. Simultaneously, we get to combine them in here. All right. So I'm going to write an equation here, and then I want you guys to help me pick this apart. This one, y equals, it's going to be a fraction. Let's say we get kx over z. Okay, x over z. Gosh, every time. Looking at this, is it clear that we've combined a couple and now it's kind of jumbled? In your minds, and I'm going to erase it on mine for just a brief moment, if I erase this part, this looks like y varies how? With what? Direct with x. So do you guys agree that on this statement, if we just look at that part, we could say right off the bat, y varies directly with x. And it sounds like a period there, but it's not. It's because there's more happening. It's combined with another type. Again, let's get real wild. What does that read? That's y varies inversely as or with what in this equation now? Careful. Look back at your example. Y equals k over x inversely as what did we say? So the denominator is what we're varying inversely with. What's in the denominator here? Z. So check it out. In this example, y varies directly with x and inversely with which variable? With z. I want you guys to write me the third statement here based on the previous two variations that we've seen. I'm going to mute my screen. If you guys have this written down, I'll pause the video, mute it, and I'll be back in like 30 seconds. Oh, I'm going to type it. So looking at this, definitely doesn't save me time. Y is directly proportional to X is the KX part, and inversely proportional to Z is the K over Z part, and we just put them together. Okay. My Zoom. Last one. Nope, not going to ask that question. Cool. We're going to use this orange color. Can y'all see that orange? Neat. All right, so far we have direct variation, kx, y equals kx. Y varies directly as x. We have inverse variation, y varies inversely as x, y equals k divided by. We can combine them directly as x and inversely as z. And we get one more that, let's just look at it. We also have joint variation. Now, I'm going to flip the order this time and just, instead of flipping it because it's going to annoy me, I'm just going to do the second and third one, the second one first, and then I'm going to make you guys pick out the equation. Now, the language here, it can be super duper ugly depending on how you want it. I'm going to say the following. Z is jointly proportional to, let's hypothetically say, X and Y. Z is jointly proportional. As we look at these, the language that I'm most concerned about is if you can physically read the difference and spot the difference between direct, inverse, and joint, you're going to be okay with this stuff as long as you have these models locked in or accessible. First off, in every other equation that we wrote, we started with the dependent variable varies with the other ones. What's the dependent variable here then? Z in this case. Z is what's being varied jointly with its other stuff. Now, instead of doing direct variation in two different ways with nth powers, the same thing can happen here. I'm going to say that it varies directly with two different things. It varies directly with x, I'm going to say to the n. You do not need to write this if you don't want to. X is just kx is fine. I'm using n for a particular reason. And it varies jointly with x and what? Y. And I'm writing to the n just to show you that it could be joint, like direct joint variation of the first power, so kxy, but it could be kx squared y cubed or something as well, and it'd say varies jointly with the square of x and the cube of y. And you would see that language show up. I just don't want to write it twice. Instead of jointly proportional, what else can we say? Z varies how? Jointly. Okay. With x and y. All right. You may or may not have ever seen this language. Do you remember doing variation like this in Algebra 2? Some of you might, some of you might not. I have no idea. You guys didn't use the books, right? You did use Algebra 2 books? Yeah. Okay. So, cool. Let's do some problems. Now, we're not going to have homework tonight, I promise. But that just means we're going to work pretty solidly for the next 6 minutes. Okay. You get to pick and choose how much you want to write. We're going to start here. All right. So let's do this one together, and then you don't have to write down the whole thing. I just want us right now. I'll write it down up here. We have more examples we can work tomorrow. Find me what you think are the most important pieces in here. We have 4 different types of variation that we saw today. Really, there's 6 if you count the nth powers as well. But there's really only 4, direct, inverse, joint, and combined. Find me the most important words here. Feel free to shout it out as soon as you think you see one, but your call. So maybe it's all important, realistically. How about with regard to modeling this, to even start thinking about it? Oh my, directly. This varies directly, immediately tells me I'm looking at what? It's not a trick question, but it feels like it might be. If it varies directly, I'm looking at what sort of variation? Direct variation. Like, I promise I'm not trying to trick you. But wait, there's more. Because not only does it vary directly with temperature, it also varies how? Inversely as the pressure. So, I'm going to make a big comment, and you're going to hear this about 20 times, maybe an exaggeration, but maybe not. When you're solving and modeling, your main goal is to pick the formula and solve for K from some given information. It's just like I were asking you to find the slope, so you could write the equation. We're finding the constant of variation K, and we're going to write it out. So, looking at this piece together here, I'm asked to write an equation relating these. A gas law states that the volume varies directly as temperature and pressure. So what's my dependent variable there? Volume. It's what's being varied with the others. So check it out. What symbol do we use for volume? What type of V? No cap. It's capital. I was just being silly. I'm sorry. It is a capital V. You're absolutely correct. I was trying to brain rot y'all. All right. Shouldn't do it there. That was a terrible choice. Capital V is equal to. Now, I see that I have an inverse, so I'm going to have a fraction, right? So I'm going to make a numerator or a fraction bar real quick. Directly as what? So I'm going to use my constant K, which we'll have to solve for. And it looks like it's T. Now, T representing temperature is capital T. If it's time, lowercase. So V volume is equal to K times T, and then forget about the T for now. We'll just pretend like it's not there, and it can actually just not be there on mine, and I'll put it back. Inversely as what? Pressure. What should we use for pressure? Capital P. Here's our equation, sort of. This is an ideal gas law. If you remember seeing that in physical science, like this exists. I don't know what you guys did in physical science. Gosh, can we make predictions with this model yet? Like, if I knew the temperature and the pressure, could you tell me the volume yet? How come, Fern? I agree. We cannot do it yet. We don't know K. Man, if only I had some information that I could plug in to find K. Like, I don't know, if I knew the pressure and the temperature at a given volume. Holy cow. Could we solve for K? To get our model, that's all we have to do. Solve for K and we'll get our model. What am I going to plug in for volume? 10,000. And equal to, still don't know K, I'm going to keep it yellow. Times, and I'm doing something that I don't like to do, but we'll talk about it. What's temperature? 360 divided by 1.9. Can I solve for K? Solve me K and rewrite the model. Right? And it looks like you guys are writing it. Solve for K. We'll jump in right here tomorrow.